So any other domains where we could use the large language model? We can try another one, because for the magic trick we need to detect the playing cards, right? Let me just see if we find a suitable picture for the playing card. So let's take which one is safe image? Safe?
Save video.
This one?
Yeah.
Okay, let's try that one. Okay, and for this, for our assignment or our hackathon, that would work quite well, right? If you give the picture to the large language model, ask them what cards are on the table. If it's a powerful model, it'll just tell you there are 3 cards on the table, and they are it even identifies the cards correctly. So now the question is, for our assignment, what will be the problem? Let's say we built a robot, we put on a powerful NVIDIA TGX or Turin or something, and we run a language model. We ask it identify the cards on the table, and it can tell you the position. I assume it because it can recognize it, it also knows where they are in the image. But for our trick, it needs to know the orientation. So I don't think it actually knows the orientation. Like that ace here would have an orientation, the club would have an orientation. Right? Actually, let's see. Um, 7 of clubs, the number 7 and the club symbols are arranged symmetrically. When rotated 180 degrees, the card looks essentially the same. 5 of diamonds. The diamond pips are not placed in a rotational symmetric pattern. Rotation changes the visual layout. No. Ace of hearts are not symmetric. The A flips orientation. Okay, so it doesn't understand rotational invariant very well. It actually got all of them. It only got the ace of hearts correct, and that would be the reason for it being rotationally invariant is wrong. So I guess we will score that as a half. So it will get like 0.5 out of 3 points for this particular question. So the zero shot approach didn't work very well with this particular co-pilot here. So let's try and change the prompt so that for this particular image here, see if you can get it to do better, and also compare it to the performance for the same question on the lava. Actually, that's not the picture that I So we can try some few shot approaches. So let's say the rotation. You can also select different models here. I think this is the reasoning model. This one. So this is kind of cool, right? Because after explaining it to the system, I just said we call cards that are invariant to rotation by 180 degrees arrow card. 7 of clubs is an arrow card, 5 of diamonds is not. Ace of hearts, now it correctly identifies why the ace of hearts is an arrow card, because it is the heart will change the orientation. So that would be an example of few shot learning, because now I had to give it some examples, and it does a lot better than without the example. And also in my experience, trying to build systems using AI, the more concrete the example is, the more other information, the more culture is around the particular feature, the large language model will do better. So abstract things like intersection of lines, it is usually surprisingly bad. But then in order to figure out which way the heart is pointing, it does need to understand lines and angles. But then when it talks about cards, it is actually able to do that quite well. So now, let's see if it does understand arrow cards. I didn't bring my deck of cards. Uh, the image of nine of diamonds. And which one is copy? Third one? Copy. This one? Okay. And I get it to list all the arrow cards for diamond. Ace of diamonds. So I made a mistake with the ace here because I'm sure
this is not there's no up down for the which one did it say? 5 it knows it's symmetrical. 3 of diamond is not an arrow. 5. I don't know what diamond is. The 9 is super. Let's take the 7 of spades. And then let's take the image and rotate it. So 7 of spades, you can recognize correctly pointing downward. So now, if we have a large language model like that running in the robot, then by sort of talking to it, you could actually instruct it about the arrow cards and the cards that you're interested in and whether they're up and down. And that's the majority of the perception that you need to do for your robot, for the hackathon. Right? The whole magic trick depends on being able to do that, right? Identifying which cards are symmetrical and not, and which ones are pointing up or down, and then one of them will be down. That's the one that the user moves. So how would you implement this traditionally without a large language model? Yeah. You would basically try and train all the cards and sort of have a specific training set. Since we know that we need to use the oriented card, like the arrow card, you don't actually need to train it on all 52 cards. It would be sufficient to just train it on the ones that we're going to use in the magic trick. But I think if you can recognize one card, that's not such a big problem. And you can certainly, if you have enough training data, you can certainly do that with convolutional neural network and a couple of max 2 layers in between. The standard kind of CNN. And we will try out later on if we can actually implement that on the Android phone so that the phone can do this. Now, I want you, for the next half hour or so, I want you to run your own experiments with the large language model. Ideally, the Lava model, or if you haven't copied it yet, then use the you can use Edge or Grok or any of the other large language models that have a here without having to download and install. Actually, do you all have the Lava memory stick now copied? No? Okay. Then so then first just start it up. When you start it, if you have a GPU and it should be able to recognize it automatically if you have a GPU. So then you want to specify the NGL, the number of layers that you want to put onto the GPU, and then specify that to 999. If you specify --NGL at the command line as 0, then it'll run completely on the CPU. On the Mac, it'll use Metal automatically. But you still need to tell it to use the let me see what it does. 7 colored cards. No, they're fine. No, not 7, 8. So it's obviously struggling with it. The lava, the model is not as powerful, not powerful enough to detect cards. So if you wanted to detect cards, then you would have to train a CNN first, and then maybe do some more reasoning based on that. The 4 gigabytes. Actually, I like the which
So if you see there, that's for a while. Yes. Yeah. Okay, good. So let's do some brainstorming. Large language models in the presentation that is extremely popular, extremely powerful. Now they have an extended tool use, which means that you can actually have the LLM call an external program, run some program for you with the result. You can get files and open the browser, all kinds of web scraping, which is something that was actually always pretty tiresome to program. So to automate the website, which of course the companies that run websites are very much against that. They don't want you to do that because they want you to look at that and collect all the data from you. So there's kind of a race going on between the people that want to access all the data and want to prevent you from being able to do that using the large models. So those applications are well known, pretty clear. The question is, what can we do with our robots? So now, when we think about the robot that we have, 2 wheels, So perception. Now for perception, there's different types of things that we would want to do that require capabilities from our system and from the so let's say we have a harvesting task, right? And we want to collect the whole parts that are littered on the playing field. Then, how would the large language model be able to help us? Let's try something else. Yeah, check the line. Let me see if that works. Actually, it won't work with anything else that works with the level, but we can use a more costly one. Let me take a picture. Okay, so it's posted sample image. And let's use the link profile. So one problem we could try would be for this particular be how many lines are in the image. If I know how many lines there are, it probably also comes very far. And then horizontally, 6 vertical lines. Not sure if but I can see why. There. Maybe I should such good show. I like yeah. Okay. It's fine. At least it's just put off the part to rescaling. So I think with the wall of water here, we would be able to get this to work somehow. We could get the we could get the number section point so we can run that to robots and that system that so without having to put separate feature section feature tracks. Assuming it's possible. So now, how did it know? So, previously, in the training data, it includes everything on the internet. Certainly, for the text models, they have also everything. So the training data, in a sense, for text systems is basically done. I mean, there's lots of new stuff that people still write on the internet, but the problem with that is that a lot of it is also generated by large language models themselves. People now generate thousands of blog posts per hour, all just based on sending a signal prompt to a large language model. it has sort of asymptotically tapered off. They're not that much better now than they were about 6 months ago, years ago. Vision, however, and audio are still more cool. But for text, they don't need that much good training anymore because humans don't produce that much new interesting text per year that would improve the performance of the language model. And for each learning system, I think that the training data is probably more important than the actual elements of the architecture. There are some small differences on the order of like 10% or so, but if your training data is not good, then your output will be crappy as well. Now, for the perception, as far as robotics are concerned, we are interested in sort of three different scenarios. So lines and corners and intersections. As well as other richer featured objects, doors, for example. Chairs. Those were actually trained on the system. And they are, depending on the training data, the detection is quite good. You show the system billions of examples of line intersections going to recognize line intersections. More interesting, I find, is the type of training data that is the type of perception, detecting objects or tracking objects that it wasn't trained on. So that would be if you're developing a team of soccer playing robots, you may want to have component pictures. Where you don't do a full retrace, but you tell the system, here are some pictures of what the other players look like in the soccer match. Make sure that you right. So then this will be one shot or few shot or one shot training or reading. Yeah. Yeah, of course. Yeah. So we want to do few shot, one shot. That is more interesting where you show the system something that it didn't know before, like what the component looks like, for Torrance Power Bridge, a picture of the racetrack with the features and the object. The system detects the features that it's looking for. And then lastly, we can have zero shot.
Window, David. Right. You have to tell me when I need to switch the camera. Okay. Reset. Oh. Okay. Yeah, that is actually the same phone. Now that I changed the temperature to 0, it simply generates the same, most likely output. And I can get the temperature way up. Then we can ask to write a poem about curtains. Here are the curtains of my life. Hang them close when night comes inside for dark. Okay, good. So we looked at perception. Um, what else could we use the large language model for in our hackathon? Yeah, and really the robot is very simple, right? There's only so many things it can do. It has a camera, it can drive around. So there's kind of perception, then there's control. So what kind of control tasks will we want to implement? Speed, yeah. Um, yeah, that kind of thing, right? Like more intelligent speed control would be useful. And um, I personally I feel that probably the best sort of application that I sort of think of would be uh, have a picture of the robot camera and then say go to that spot which is in that image, like a particular cross intersection, and say I want you to drive there. That would be quite useful too. That in itself is not a difficult thing to implement, but you would have to implement it in order to make that work. And of course, with that reckoning, the spot doesn't really need to be in the image. Right? Like if you can control the robot 10 degrees to the left, 10 degrees to the right, it doesn't actually need to see where it's turning. But I think for the LLM feedback system would be. Now, today we're not really set up for doing that kind of thing, but let's try and see if we can convert that to a text description and then just try out the text description on the system. And I think one of the crucial abilities, skills, or features of intelligence is if I ask you a question, one minus two, three, minus four, five, then what's the next number? Minus six, and why? There's a pattern, right? And I think that is actually at the heart of, at the very core of human intelligence. I doubt that we're running dot products continuously, but the ability to predict things, I think, seems to me to be fundamental to any kind of intelligence. I don't think you can actually act intelligently unless you're able to predict about what will happen to the world, right? What possible future world states there are, what world states that are likely. It won't be impossible to act intelligently. And this kind of pattern recognition, being able to detect the pattern, and humans are quite good at that, and then being able to make the next prediction, I think that would be something that if the LLM can do, then it would have at least some kind of primitive reasoning capability. So now, if we actually try that on your Lava system and Bing, and see whether it can recognize this particular pattern. Now, since we're asking it for numerical answers, probably you want to bring the temperature down a little bit. Instead of 0.7, you can make it 0.2. I think it's usually not recommended to set it to exactly 0 because on average performance is better if you have at least some randomness.
Okay. Uh, yeah, that's actually pretty cool. Now that I keep the temperature to zero, it will be most likely. And I can get the temperature way up. So we put out right off the curtain. Yeah, the curtains open. So okay, good. So we looked at perception. Um, what else could we use the large language model for in our yeah, and really what's very simple, right? It's only things we can do with that camera, right? So there's kind of perception and there's control. So what kind of control tasks will we want to speed? Yeah. Uh, yeah, that kind of thing, right? More intelligent speed control would be useful. And uh, I personally I feel that probably the best sort of application that we could sort of would be have a picture of the robot camera. They go to that spot to either that it's like a particular cross intersection And of course, with the recognition, you can spot that to be in this. If you can control the robot 10 degrees to the left, 10 degrees to the right, so you can see at least feedback system. Now, today we're not really set up for doing that kind of thing, but let's try and see if we can convert it to text description, and let's try out the text description on the system. And I think one of the crucial, for me, one of the crucial abilities, skills, or features of intelligence is if I ask you a question, one minus two, three, minus four, five, then what's the next number? Minus six and y. There's a pattern. And I think that is actually at the heart of, at the very core of intelligence. I doubt that we're running dot products completely, but the ability to predict things, I think, seems to me to be fundamental to any kind of intelligence. I don't think you can actually act intelligently unless you're able to predict about what will happen to the world, right? What possible future world states there are, world states that are like, it will be possible to act intelligently. And this kind of pattern recognition being able to detect the pattern. And the humans are quite good at that. And then being able to make the prediction. I think that would be something that if the LLM can do, then it would have to be some kind of primitive reasoning capability. So now, if we try that, actually try it on your laptop system and see whether it can recognize this particular pattern. Now, since we're asking for answers, probably you want to bring this down a bit instead of 0.7. You can make this 0.2. I think it's usually not recommended to set it to exactly 0 because on average the performance is better if there's some randomness. Yeah. But not mine is the PC got that. You got my oh. One plus one plus 4. 4 plus 5 is 9. 6. Yes. Okay, but it's a pretty big context there. So, yeah. Right. If you have the type waveform of the doors, right? Doors, or anything. Okay, let's go to your terminal. Capsule is control C. And then starting with the PDO low cost. Like, no, this. Right. Here, it's more C plus plus. I just want to make sure it's okay. Or and then on the you also have to specify so sorry dash yeah. No. Uh,
Good work. matey, we'd be doing an Ace of Hearts trick here today. You can't see it now, but I'll make your jaw drop when you see it disappear. So gather round, let us commence this magical feat. Here you go. Step one, take a deck of cards out of your treasure chest and spread them on the table like a bountiful feast for them. So that's doing a reasonably good job. Right? And then it just goes through. So that kind of thing, high-level human-robot interaction, the large language models can do very well. You can combine them with speech recognition and speech generation, and it'll be able to do a good job just talking to people rather than the text interface. Yeah. So clearly that will work. But that's not so hard to program, even if you do it by hand, right? You could ask people to write something, run it through the speech generator. There's not much interaction there with the people. Like he's just reading that whole text out. If you want it to be more interactive, I think the large language model would help. Where I'm not so sure is the actual control and navigation, the kind of thing that is really hard to program, that we would like to use the LLM and then I can just tell it. I think that is significantly more, requires more thought, maybe possible typing it into the LLM, how you structure how you map it to language. And then things like balancing for humanoid robot, just tell the robot get up and walk to the door. That's not going to work. I'm pretty sure that's the pipe dream. But again, then humans can't do that either. It takes little babies about a year to learn how to walk and move their limbs accordingly. So, and of course, there are some extremely a lot of very interesting research is going on with humanoid robots at the moment. I just saw this one today, which I think is very cool. So here they're now playing tennis with the humanoid robot, and it's doing a pretty good job. Like 2 years ago, I would have thought this is impossible in the next 10 to 15 years. But it can now really, and I mean, obviously these are not professional shots, and he's kind of serving it nicely to the robot, but still, it's able to return the ball. Yeah, and playing tennis is not so easy, and to get from zero to that stage is the really tough part. To get from there to performance like, I don't know who's the number one tennis player, the McEnroe or some a professional tennis player, is sort of a lot more fine-tuning than this. Fundamentally, I think this is the really hard first step. So I just saw that today. Really impressive. So this is done by taking motion capture data from human players and then mapping it onto the kinematics and dynamics of the robot, which is using reinforcement learning, which is sort of the state-of-the-art action generation framework at the moment that works really well. There's lots of progress. Actually, it looks like the racket is a little bit bigger than normal, doesn't it? Oh, good shot. That was a nice one for. Anyway, there in that kind of domain, learning how to play tennis is not something that the language model will be able to do well. Then, any other interesting sequences that you would like to test? guess we could do this with two-dimensional coordinates, right? Because really our robot has two dimensions. So we could do like 1.0, 0, like do the prediction on two coordinates at the same time to get the straight motion going. See if that works. One point two, 4. Oh, now he's still speaking like a pirate. And obviously pirates can't do math. Yeah, this one at least you can do 1, 2, 3, 4, and then odd numbered integers starting from 1. Okay, the answer is numerically correct, but what it says here doesn't make it. Yes, we'll take it correct. What's the next? Four 4.8, yeah. 4.5. Should have just stopped after 4.8. And then what did I have? 18. 4.8. 26. 34. 05. I think Copilot. So for the Copilot, this is an easy trick. You can do that. Okay, good. Then that's it for today. And we'll have the afternoon class with the German students. And we'll do another assignment so that you have a chance to get to know them. And we'll be looking at PID